ANPers, this is Dr. Jones checking in. This is ANP2, Lecture Test 1, Video 11, covering Notesets pages 23 and 24. So, here we are again. Nystagmus, top of page 23. Nystagmus is trouble controlling your eye movements. Now, this can be caused by brainstem or internal ear damage. And it shows a problem with equilibrium. So how you test for nystagmus, you know the whole H thing you do to test for the extraocular muscle movements? So on the long middle bar of the H, excuse me, you are looking for a nice smooth movement back and forth. With nystagmus, you'll get a jerky eye movement, and I'm going to make a jerky finger movement so that I will make a jerky eye movement, because if you don't have nystagmus, you can't pretend. Okay, so that is nystagmus. Just a second. Excuse me. I just heard Rex the rooster crow. I don't know if y'all can hear the roosters when they crow, but super cute. Okay. Sound waves, as we have discussed, are compressions of air molecules. And if you're curious, this is what I was trying to draw that time I drew all the dots. So they're compressions of air molecules with spaces between them. So every sound you've ever heard, me, your favorite music, your mom, your kids, significant other, all of those things that you can tell via sound, you're responding to compressions of air molecules. Okay. And oh, we should say that they're waves of pressure conducted through a medium, be it, air or water or some such. So the pressure waves are the regions where the air molecules are crowded together or farther apart. The wavelength is the distance between two adjacent peaks. Adjacent means next to each other. The peak is the top peak. Oh, and this is peak, P-E-A-K, like peekaboo is P-E-E-K. Spelling matters. The wavelength, we said that. And then cycles is just the physics term for a wave. So each of these is a wave. Although since we're going from peaks, probably this way is a wave. And that is a wave, which is a cycle. The frequency is the measure of cycles per unit time, the measure of waves per unit time. And the frequency measurement that we use is hertz, and that's capital H, lowercase z. And that is the cycles per second, so the number of waves per second. So it is a measure of frequency. What's a frequency, Kenneth? The pitch is high or low and is an indication of the wavelength. A high frequency sound has a high pitch, and has a short wavelength. So if we've got a wavelength of 0, a high-pitched sound will have a wavelength of 15,000. And anywhere in this end of the spectrum is going to be a higher pitched sound. A low frequency sound is low pitched. Here's our number line. It's all about the number line. See, if that's 15,000, then that's 10,000. Then that's 5,000 thirds. Ugh. So low pitch sound would be 5,000, 4,000, 3,000, 2,000, 1,000. Low pitched would be about 100. So you can see that this end of the spectrum is low pitched, and this end of the spectrum is high pitched. Oh, and low pitch would be like low pitch. Amplitude is the height of the wave from peak to trough, from top to bottom. Amplitude in sound waves is a measure of intensity, and intensity is a technical term for volume. So the amplitude is your volume, your intensity. Decibels is a measure of amplitude. It's abbreviated lowercase d, capital B. Deci means 10. That's a B. I don't know. I'm writing with a mouse. Sorry. So the measures of decibels, I believe I have on the next screen. 0 is the lowest audible. 30 is a soft whisper. Conversation will be 60 decibels. 120 is a rock concert where you are in immediate danger. So wear your earplugs to go to rock concerts. You might not care now, but if it's the difference between going deaf at 80 instead of going deaf at 60, 20 years of not actually hearing what people are saying to you and having to pretend. Yeah, wear the earbuds. Okay, so describe a sound measured at 15,000 hertz. That was, hertz is frequency, frequency is pitch, and 15,000 hertz is high pitched. And 140 decibels is very loud. So high pitched and very loud. Describe a sound measured at 100 hertz and 30 decibels. 100 hertz is low pitched, and 30 decibels is a quiet library, very soft. And give possible frequency and intensity measurements for a quiet. So which one's quiet, frequency or decibels? Hertz or decibels? Quiet is decibels, the amplitude. So give me a number for quiet. Yeah, anywhere in here is pretty quiet, 30, 50. And then high pitched, we said 10,000, 15,000 is high pitched. Here it is. And possible frequency and intensity measurements for loud. So which was loud? Decibels and the bigger number. So a loud, low-pitched rumble, like a chainsaw, is 100. That's pretty loud. And then low-pitched is your frequency. And so we said low-pitched. We gave a number, 100. Anything less than 1,000 is going to be very low-pitched. Okay. Excuse me. Bottom of page 23. Sounds are waves of pressure in the air. The auditory ossicles convert sound waves in the air into mechanical motion, which they then transmit to pressure waves in the perilymph of the cochlea. These pressure fluctuations in the perilymph are detected by hair cells in the spiral organs. Next page. And then we have a chart. Let me find our chart. There's the chart. Okay. So the cochlear duct is the scala media. This is just the English term, and the scalas are the Latin term. Scala means duct. The cochlear duct / scala media is part of the membranous labyrinth. All of the membranous labyrinth contains endolymph. Key features here are the spiral organs and the hair cells. The vestibular duct is the scala vestibuli. bony labyrinth, perilymph, and the vestibular duct has the oval window. So when sound enters the cochlea, they enter at the oval window of the vestibular duct. And the tympanic duct is the scala tympani, also bony, also peri. I want you to see on this picture that the vestibular duct and the tympanic duct are actually continuous at the tip of our cinnamon roll spiral. So they are both bony labyrinth, they are both perilymph, they are the same. The difference is that they've been folded around sort of that cochlear duct, and so by folding it, we have created two different locations. And so scala tympani, the tympanic duct. And it contains the round window, which allows these excess vibrations out into the air of the tympanic cavity. Otherwise, as you age, the round window can kind of ossify on the edges and not bulge very well. And then these sound waves get caught, and then you get like echoes, audio echoes, and it makes it hard to hear, hard to distinguish sounds. Okay, and then the basic 6 steps of hearing. We had that conversation. Okay, and then here's what your cochlea looks like. Again, cinnamon roll spiral. So these are the same tubes just spiraled up, and you're just cutting through the cinnamon roll to see all the different layers of cinnamon sugar goodness. It's about time for cinnamon rolls, isn't it? Okay, so the cochlear duct is in the middle between the vestibular duct and the tympanic duct. Here's the cochlear duct between the vestibular duct and the tympanic duct. It's the cochlear duct in the middle. And the hearing receptors or hair cells are in the spiral organ, which is this part here. And again, it's called the spiral organ because it's spiraling around. Okay, so here I always start with the vestibular membrane because it's fairly visually distinct. And above the vestibular membrane is the vestibular duct. Under it is the cochlear duct. There's a line here, which is the basilar membrane, and under that is the tympanic duct. So here's the basilar membrane, under that's the tympanic duct. And here we've zoomed into just the spiral organ to show the basilar membrane, tympanic duct, cochlear duct. So in the cochlear duct is the tectorial membrane. On the actual slide, you can see that when it dries out, it kind of curls up like a little elf toe. Those are so cute. Tectorial membrane. When they're not dried out in life, they look more like a tongue. But again, this is a tongue that spirals around, so it's more of just a membrane, but it still looks like a tongue. So what happens is that, and we're about to write all this down in the 6 steps. The sound waves come in. I didn't already say this on one of the previous videos. Okay, a brief version then. The auricle or pinna funnels the sound into the external acoustic meatus, where the tympanic membrane, the eardrum, turns that sound wave energy into mechanical vibrations of the auditory ossicles, which in order are the malleus, incus, and stapes. The base of the stapes is an oval. It sits on the oval window. So when you hear something that causes the base of the stapes to rock on the oval window, the auditory ossicles also amplify the sound. And that creates sound vibrations in the vestibular duct, the perilymph of the vestibular duct. Now, this basilar membrane gets thicker. It's like a giant wedge, and it gets thicker as it goes through. So with the high frequency vibrations are closer to these windows. And when the vibration gets to an area of the basilar membrane whose vibration, you ever like vibrate something, it kind of, you hit that kind of resonance? When it hits that kind of resonance spot, it vibrates that region of the basilar membrane and then travels out through the tympanic duct out the round window. So let me show you a better picture of that. We already had that conversation. Okay. Let's write down these first three basic steps since we're here. Number one, the sound arrives at the tympanic membrane. Two, that causes vibration of the auditory ossicles, which amplify the sound. Three, the stapes transmits those movements into pressure waves in the perilymph of the vestibular duct. There's the next slide. 5, the pressure waves distort the basilar membrane on their way out. That was 4. 5, the vibration of the basilar membrane causes the hair cells to bump the tectorial membrane. I have a picture. And 6, the information about the region and the intensity, which is our volume, of the stimulation is relayed to the CNS over the cochlear branch of the cranial nerve 8, the vestibular cochlear nerve. Of course, the vestibular branch will carry information about equilibrium because it's from the vestibular complex, the vestibule and the semicircular canals, which do static and dynamic equilibrium. But hearing goes over the cochlear branch of cranial nerve 8, the vestibulocochlear nerve. There's a different picture. There we are. So when you get to the area where this basilar membrane here vibrates, sitting on top of the basilar membrane is the spiral organ, which is this whole region where you hear. And so as this moves up and down, it moves the hairs in relation to the hairs of the hair cells in relation to the tectorial membrane. So when it bumps up, those hairs bend. And as we know, the cell membranes of the hairs of the hair cells are studded with mechanically gated ion channels. So every time the hair cells bend, that bends the cell membrane, opening those mechanically gated ion channels, allowing ions in or out of the cell, either or depolarizing or hyperpolarizing that receptor cell. And that changes the chemical transmitter released across the synapse to the sensory neuron, whose cells will be in the spiral ganglion. So here's a corner of the spiral ganglion, which again spirals around because this whole thing's a cinnamon roll spiraling around. Everything's a spiral. It's a spiral. Okay. So the number of, if you activate all the hairs and all the hair cells, then you know you have a particularly loud noise with lots of intensity because it caused more physical vibration. All the hairs bent instead of just a few. Okay. So that's how you read the intensity. There's a keyboard arrow. There we go. And this shows that the different regions of the basilar membrane vibrate at different frequencies. And then this picture shows that the high frequency vibrations at the beginning are read here. The mid frequency vibrations in the middle are read in the middle, and the low frequency vibrations read at the tip of the spiral are read in their own section of the brain. So if you were doing neurosurgery and you had a patient awake and you zapped them right here, they would hear a high frequency sound. If you zapped them right here, they would hear a low frequency sound because, like all sensation, your perception of it is in the brain. Okay. Okay. Yeah. So that's the auditory pathways where it activates the surface of the brain tells you what kind of sound you heard. Okay. And that should be it. Yay. Okay. And so this is a picture from several years ago when my children were still small. They were huge at the time. Looking back, they were tiny. And this is my parents, and that's my mother taking pictures of my children because the majority of the pictures that I have of my mother, she's taking pictures of my children. So that's how that goes. This is in Port A, Mustang Island, which incidentally is where my husband grew up. So, okay, so that again finishes lecture test 1 material. Yay! So this has been a video lecture for ANP2 lecture test 1. This is now lecture 11, covering pages 23 and 24 of the note set. I appreciate your patience through all of our tech issues, and thank you as always for tuning in. The education must go on. Dr. JF. Oh, my note set's on my keyboard, so I can't Command Control Escape. Thanks again, y'all.